Hi. I'm going to do this slide list, so at any time you have a question, or want to heckle me or yell out, just do that, and we'll roll with that. Basically, I'm going to talk about the high-level problems that drive the design of secure scuttlebutt. So a few years ago, I had this revelation about what I called, some of Substack with influence here, cipher links. So a cipher link, well, it's when you address an object with its hash. It's kind of like, call it cipher link is like a reference to hyperlink, where a hyperlink tells you where to get a thing. So it's like on this server, at this location on that server, that's the thing I'm talking about. And that means that to get that thing, you have to go to that server to get it. And that gives that server quite a bit of power. On the other hand, a cipher link tells you what to get. It's like of all of the things in the universe, the thing I'm talking about has this hash. So it doesn't matter who you get it from. If anyone gives you this thing, you know that that's the thing you asked for. So, and I sort of realized that all of the successful and secure peer-to-peer systems already works like this. So BitTorrent has an info hash which uniquely identifies from all the torrents in the universe, this is the one I want. Bitcoin also does exactly the same thing, where you have like transactions and blocks and you point to the previous thing, and it's like that's just how that works. And that BitTorrent and Bitcoin are just very simple data structures out of that we've created so far, but like Bitcoin is a linked list, that's all, and BitTorrent is a hash table, that's all. But those are the two of the simplest data structures, and there could be this whole other cornucopia of other data structures somewhere in between those two extremes that could be useful for other kinds of applications. So I got really interested in, I wanted to build this sort of arbitrary data replication thing. So you could create, first of all, like mutable structures. So like, let's say you could build a wiki or something like this, or you could make a blog post and have like, just by having objects that link to other objects and create any kind of structure and replicate them, and then you could build arbitrary peer-to-peer applications through this thing. And I started exploring this possibility, which is like the first of the problems that's driving the secure scuttlebutt design is replication. So replication is basically about you compare two data sets and then figure out what's different and then send the stuff that was missing so that now we have the same data. So you can think of BitTorrent like this. So you have a BitTorrent file that has the set of all of the blocks and you know what the hashes are, and then you just send a bit field that says whether or not you have that block, and then you can instantly just send the bits over. But BitTorrent is limited because it only does static files. I wanted to be able to do arbitrary structures, and I explored this thing called a Merkle tree, where you can sort of, in a couple of, you have to round trip a few times, and you figure out what of a flat set is missing. And as I delved more into this, I was like, the performance of the Merkle tree comparison wasn't quite as good as I hoped. In the good cases, it was efficient. In the bad cases, it had to send a lot of round trips, and round trips are really painful. This is informed by growing up in New Zealand. My parents have satellite internet, and this is really good. This was the best internet you could get on the farm, and it had latency is like 1 second to do a round trip. So if you're doing more than one round trip, it's like you don't want to be there. Instantly, that's about what the round trip time you would get if you lived on the moon. So, in fact, if you lived on the moon, you can't get better round trip than that without time travel. So I don't think that's... for space travel, we need good data replication anyway. So then I stumbled upon this other system called Cryptosphere, which is made by Tony Aseri, I think is how you pronounce his name. And he was building this file system where peers talk to each other, and then they had this sort of this credit system. They would make IOUs for each other, be like, I'll store this for you, if you store this for me, then they come back later and check on this thing. And I'd actually sort of been exposed to this idea before from David, and when we spoke at PeerConf, which was kind of the first in a series of conferences that have all had different names, but have had a common thread running through them and have led to this point. This is like the fourth one now. And I was like, so Cryptosphere has a log keeps logs of who they interact with, and then it replicates those logs with the other things, and then builds the file system on top of that. And I was like, oh, logs. It kind of sounds like Twitter, and incidentally, because the peers are interacting with each other like humans do on Twitter. And I was like, hang on, humans kind of like using Twitter. Why don't I just build that? And suddenly I realized this would be really easy to do, much easier than the arbitrary data structure replication, or just make the simplest structure, which is just an append-only log, and then you can follow each other and replicate those as well. And it really maps to social networks, which people seem to be addicted to. So it seems like a good adoption story as well. It's like you could build this, people will use it, and then like the decentralized search, I was thinking about that, and I was like, that's a really hard problem. Like, how are you going to do that so that everyone knows about this stuff? But a lot of content that people get is just shared over a social network. So you could still get discoverability by a social network. So you could do things like index torrents like that. So you could just see, like, here's the torrents my friends have and the ones that their friends have. So it seemed like it would have plenty of applications. And by having being based on a social network means that it solves the second problem, the Sibyl attack problem. Now, the Sibyl attack is like the most important problem in decentralized systems. The Sibyl attack is basically, it comes from a psychology book about a woman with multiple personalities. And the question, so the Sibyl is like, how do you, her name was Sibyl. And so how do you tell if a given key, normally a public key is the identifier for a user or a node in the network, how do you tell that key is actually a real person or a real computer? And because you could just generate 1,000 keys or 1,000,000 keys, you generate as many keys as you like, how do you tell which ones are real and which one isn't? And basically it's the same as problem as spam, really. It's really easy to send an email. So you can send emails you can just send all the emails you like, but then you need to filter out the ones that are nonsense. So there's a bunch of approaches that you can use to make this decision. So one simple one is you use some token or other to make it expensive to create a identity. For example, if you are writing a system that like takes votes over the internet or something like this, then the easiest thing to do is have one vote for IP address. This is relatively simple. The cost of getting an IP address, if you're clever, you can easily get IP addresses, or you can spin up new servers on Amazon, or you could run, if you have a botnet, then you can have all of the IP addresses you like, and consequently, these voting systems are pretty unmeaningful. Like a few years ago, Moot, the founder of 4chan, won Time Man of the Year online poll, and then all of the other candidates, their first names, the first letter of the first name actually spelt out some message from 4chan. Marble cake, yeah. So the Time Man of the Year online poll means nothing. And then they just choose who they want to be the Time Man of the Year, or Person of the Year. Another case is like email spam. Email is basically unsolicited messaging. If anyone has your ID or your email address, they can just send you anything they like. So it's kind of not very good because your email address leaks out and then people send you nonsense and stuff. So you use this. Eventually people sort of figured out a reasonably good method of detecting spam, which was pattern matching. So you build a model, a dynamic model, where you tag things as spam or not spam, and then when a message comes in, you compare it to the other spam and be like, yeah, this looks like spam, we'll throw it away. Or put it in the spam folder, we'll ignore it, unless, occasionally this causes problems. One time I booked a flight and then the flight confirmation went to my spam folder, and I got lucky when this ended up only costing me $200 to cancel the flight after I'd bought another flight. But it could have been like $1,000 because it was like a return flight from Singapore to New Zealand. So that was a very expensive false positive. False negative. A very expensive mistake for me. And it's also this cat and mouse game where the spammers just get better at making spam that looks like real email, and the spam folders have to get better and better. And so that works okay. But what works even better than that, and is simpler, is so Twitter basically doesn't really have the same problems with spam that email does. In a way, it's like of the. I saw this website that would tell you how many of your Twitter followers were real, and I tried this, and it said it basically doesn't do anything very sophisticated, just by like the kind of pattern of how they post, and like how old their account was created and how many followers they have and stuff like this. So it was unsophisticated fake accounts. Said I had about 15% fake followers, and this seemed to be pretty common around other people I knew. I saw one guy I knew had like 85% fake accounts, so, but I'm not going to say who that was. But you don't experience much spam on Twitter because Twitter is what I call a solicited spam system. So you only get messages that you've asked for. So you follow someone and then they can send you all of the nonsense that you like, but it was your fault because you asked for it. Email, on the other hand, you have to unsubscribe from the spam. So I unsubscribe from newsletters every day, and I'm not sure how I get so many. I sort of noticed recently that a bunch of the spam emailers I was getting thought my name was Tiffany. I have no idea how this is the case, but now I have a Gmail filter for if it contains the word Tiffany, then it just moves it into the spam folder. I don't know anyone whose actually name's Tiffany, so this is a problem. This isn't too much of a problem for me.
That's why you don't know anyone named Tiffany, though.
No, I only did this like last week. Yeah. Tiffany Airlines. Yeah. Where do they operate from? I think I'll be okay. Yeah. So when you follow someone on Twitter, it's actually quite a big deal. Like you're saying, of all of the people on the internet, you are definitely a human. Probably a human or a very entertaining dog or bot or something like this. Like it's a big deal. Like you probably only follow like a few hundred, maybe 1,000 people out of the millions of people who use this thing. So it's like you're actually saying quite a lot there. And turns out I later learned that Gmail actually does the same thing. There's no explicit like friend or follow relation in email, but there's an implicit one. And so Gmail actually parses the social network from email and then uses that to detect spam. And so how you friend someone on email is you reply to their email. So if you reply to their email, then they'll be like, oh, these people like have a real relationship on some other level. So if someone that this person knows this person knows this person, that sent an email to this person, it's probably good. And this is a really easy mechanism to implement. And if you just have so secure scuttlebutt, you follow the people that you want to replicate, that you want to get the data from. And then the system, just to make sure the network is sort of full of stuff, it replicates the people you follow and the people they follow. And this pretty much eliminates the Sibyl attack. Because to get data, you can generate a whole bunch of fake accounts, but you can't get anyone to follow them. Well, to get them to follow them, you have to get a real human to make that call. And that makes it much, that's actually pretty difficult to fool. You fool some people, but you're not going to fool everyone. And maybe you fool one person, but you don't fool their friends. So they can be like, nah, don't follow that one's nonsense. And so you end up with pretty good stuff, but without having to do anything really clever, just by the architecture is just naturally resistant against Sibyl attacks. So really what you get is a trust system. And that's kind of the really interesting thing about what is in Twitter or Facebook or something, is they have this implicit trust system, trust network, where so you vouch for these people effectively by being willing to receive their nonsense, and then but because Twitter and Facebook is like a closed system where all of the things live in one place, that the gatekeepers can basically control who is able to build things on top of that. And I think that limits it substantially. So look at Twitter. Twitter is an application for sending 140 character messages. But if I open it in my laptop and scroll down, it starts going slow. It's I don't know how they are so incompetent, but it's really painful to use Twitter. Since a couple of weeks ago, it was bad before that. Then it got worse, and it's just I can't use it on the web anymore. I need to upgrade my computer to post 140 character messages. And it's that's if this was an open source project, I could post an issue and maybe fix it, but I can't do that because I'd have to work for Twitter, and well, I fear that I would go in there being okay, I'm going to fix this, and I'd find out why. Yeah. And I'm not sure if I want to know specifically why it's so hard to make a 140 character thing when you have thousands of engineers. So instead, I was just so happens that because of the design of this thing, it would actually be pretty easy to make a peer-to-peer version of it. You just map the networking connections over the human social connections, and you'll end up with a good network topology that will have the right properties and prevent Sibyl attacks. So it's this is just a really simple, dumb idea that will probably work. That's kind of that's the where and why of Scuttlebutt, secure Scuttlebutt so far. We're currently working on we had all these big ideas for things you could build on top of it, which we'll get to in a second, but we're currently throwing all those away. Well, putting all those on the back burner and just making it simple and work really well, and just have a few properties just have better security, point-to-point encryption, and end-to-end encrypted messages. And then there's a lot of, in the next generation, a whole bunch of amazing things I think we could build on top of it. For example, basically you have this trust network, and trust is really interesting. You can pretty much solve all the problems you can't solve with a blockchain, you need trust for. If you need something like running servers for your thing, that's a very high trust situation. Trouble with a blockchain-based thing is, one, everyone ends up with all the data, and two, if you want to do a new kind of thing, Like you need, instead of a proof of work, if you want to base it around storing files, you need to have proof of storage. If you want to have execute code on computers, you need to have a proof of running code correctly. So basically you need to invent new computer science for each kind of new application you want to build on top of the blockchain. And computer science is really hard. But if you just have a trust system and be like, well, who can I trust? That is simple. You'll be like, well, I can trust this person. They can run code for me. And then sooner or later, if they are doing something dodgy, you'll find out. Maybe you get 3 other people to do it as well. Then you can trust but verify. And then that's much simpler. You can sort of apply this trust hammer to way more nails than you can a proof of X hammer, because that hammer is very sharp and pointy and only works with one kind of nail at a time. So as I have talked to people about trust systems, I found that people have quite divergent intuitions about what trust is. So I think there's two, because trust is obviously very important to being a human, but it's something that people don't really think about. They think about who can I trust, what should I trust, but they don't really spend much time thinking about what is trust. But because of this, I've started thinking about it, and what I think is that, well, on one level, trust is it's a belief that someone is neither malicious nor incompetent. You need to have both of those things. However, not malicious is much easier to achieve. I'm pretty confident that most of the people in this room are not malicious. Certainly all of the ones that I personally know, not malicious. However, incompetence manifests itself quite differently. Like, I know that I have some level of incompetence and even only trust myself to be competent to a certain degree, like say 89%. And because of that sort of distrust, it means that, like, I get to the airport extra early and I leave a toothbrush in my bag so that when I do remember, I can brush my teeth and so on like that. I have lots of nice friends who are a little bit incompetent. And this has sort of important, like, security applications and stuff like this as well. You might trust someone not to be malicious, but they could still, because of incompetence, become compromised by someone who was malicious. Psychologists estimate that the level of psychopathy in society is about 1 or 2%. So that's like 1 in 100 to 1 in 50 people are malicious. Everyone else is just varying levels of incompetence. That's the saying, don't ascribe to malice what incompetence is, when incompetence is sufficient explanation. Obviously, occasionally, malice likes to pretend to be incompetence. So you need some way of finding which keys are definitely controlled by competent, non-malicious peers. And then you can do all kinds of things. Like, trust sort of creates as a kind of value. And unlike money, because you issue your own trust by behaving in a way that people know that is reliable and non-malicious. This is like the next level stuff, but you could build some kind of currency-esque system on top of trust and IOUs, but that's like the second system. Okay, so how am I doing for time? 5 minutes? Okay, so I've got 5 minutes. I've got another idea I've been thinking that I want to talk about. So, in building Secure Scuttlebutt, we needed this. We want to have end-to-end encrypted messages, where you post a message into thing, and then only the intended recipient can read that. But also in the general messaging, like it's sort of like Twitter, so you publish a lot of stuff, but you don't want a passive observer to be able to see what you're saying, and you don't want and like thing that we've realized recently is content is actually kind of hard to analyze. So actually protecting the content of messaging is relatively important, but it's not that important because it's actually one of the most interesting pieces of information is the metadata. Who was talking to who? Well, it's the same as the social network. So you don't want to leak out the graph of who's emailing who. That should be relatively private. Like the people who you trust should get to find out who you trust. But if a random person comes up to you in the street and it's like, who are all of your friends? You're not going to tell them. Because if you are stupid enough to tell them, they'll be like, oh, well, this guy's an idiot. And because he's an idiot, it's probably not worth robbing. But probably all his friends are idiots too. So we'll go rob all of them as well. And you don't really want to have people like this that are this incompetent in your social network. But applying that intuition, I think since people are peer-to-peer networks themselves, you have naturally quite good intuitions about the security properties that would be desirable in such a system. So we want to not leak information like that. So TLS, for example, is not very good because it sends the public keys in the clear, so an eavesdropper can easily see who's talking to who and correlate things. It'll be like, there's map these relationships, and then they'll get the topology of the network out. And then if one public key is causing trouble, it would be easy to find out what peers that server is on, where it's traveling around, and then just attack that thing. And given endpoint security being so weak, you'll probably get in and compromise that thing, and then you can read the end-to-end messages and blah, blah, blah. So had the sense that we needed a new secure channel protocol. But there's the crypto taboo of don't roll your own crypto. And just crypto is very scary. So I sort of really sense this need for new crypto to exist. But how do you do it safely? And I think crypto is kind of like, climbing Everest or sailing across an ocean. Like, it's dangerous, but you can do it if you're determined and do it correctly and know what you're doing. You just have to learn how to do it and then progress properly. So I started studying how all of the various secure channel crypto protocols worked. So I just collected all the things I could find. So there was BitTorrent obfuscation, there was SSH, there's TLS, there is Curve CP. I also looked at the secure channel from IPFS, which is similar to, it's a simpler TLS. And I sort of studied these, and I went through and just made like Alice and Bob stories about how each one worked. And then analyzed like what would happen in different kinds of attacks and stuff like this, and what properties they had. And as I was doing this, I sort of realized, oh, hang on, this is like a process that you could apply to any kind of crypto primitive, any kind of crypto protocol. It's like, and what's missing from cryptography, from the practice of cryptographic engineering, is a software engineering practice, such as test-driven development. So in test-driven development, the rationale is we want to make sure the code is correct. Also, we need to know that the code is correct. You can have correct code without tests, but you don't know that it's correct unless you have tests. So we decided this is the most important thing, so we'll just A, test everything, and B, write the tests first to make sure that we have tests, because we don't quite trust ourselves. If we get something that's working, then we'll be like, oh, we can't be bothered writing tests for it. So we'll write the tests first. And with security systems, with cryptography, we need to know that it's secure. And the only way we know that it's secure is by auditing it. So what if we instead let the auditing drive the design process? So we'll audit first and then implement later. So I sort of realized I was doing this, and I was like, oh, I'll just write down, describe what I'm doing. So first study you want to design some protocol, study all of the analogous protocols, figure out what properties they have. By properties, I mean things like what information is available to different parties in the system. So we have Alice and Bob, we have Eve, who's an eavesdropper, we have Mallory, who's a man-in-the-middle attacker, you have Sydney, who can do a man-on-the-side attack, like flip bits, and be like, what kinds of information or behavior can these different parties get out of the system? Those are the properties. So, for example, in TLS, Eve can see who the server is and who the client is if they have client certificates. Following like telephone intuitions, I realized that there were some things in a peer-to-peer protocol be different. For example, in TLS, when you connect, the server answers the phone and says their name. So it's like Bob's Pizza. And that's perfectly fine if you're running a business. You want everyone to know who you are, and you want to accept calls from everyone. But if you're an individual person, if someone calls you, you don't want to answer the phone and be like, Dominic Tarr speaking, because then the telemarketer just updates their database, and next time they call back, they can ask for me personally. And I'm like, oh, you know me. Oh, I guess you can talk to me. What else do you want to know? And you shouldn't let that information leak. You should make the caller authorize themselves and prove that they knew who you were and had a legitimate business calling you. So they should send a message to you to say who you are. And the closest one to do this was this other protocol called CurveCP, which was designed by DJB. But having analyzed all of these things and I looked at this, I found it had a few interesting properties that I would term security leaks, not a security hole. Like you couldn't compromise the system because of this, but you could get some information out of it. And one thing that CurveCP did was it encrypts the first packet that you send to the server to that server's public key. That means that only the server can read that message. But this is actually not a great idea, because the first message, you don't know who it's from. It could be from a replay attacker. You need to respond to them, and they need to sign a nonce before you know that it's not a replay attack. So because the first message is encrypted, if I live on this server, then someone sends a message to me that only I can read. If I respond to that, I've basically confirmed my identity. As the same as last time. So if you send this message to me, I go to a different IP address, someone sends a message, the attacker resends that message to that server, I respond to them, then it's like, oh, obviously it was the same key. Replay attacker is the lowest of the low, and they shouldn't be able to get any of that information, shouldn't be able to get anything out at all. So in the first message, I don't think you should send any, it should just be a random number or a Diffie-Hellman public key. The other thing I found was weird was it uses CryptoBox, which uses a Diffie-Hellman style but with elliptic curves to generate a shared key between two key pairs. So this is different. There's like three things you can do with asymmetric cryptography basically. There's signatures, there's decryption, and there's shared keys. So with the shared key exchange, you can take my public key and your private key and make a shared key, or you can take my private key and your public key and make a shared key. And they'll both be the same, and then it's easy to have symmetrical encryption after that. But it has this weird problem if you use it for authentication, because in the case of key compromise, so key compromise sounds like a distant edge case, but if we're talking about forward security, then key compromise is within, we are talking about what happens if the keys are compromised. And for forward security, if the keys are compromised, you want to make sure that the compromiser cannot read the old messages. So it should at least fail safely. They're going to be able to read the new messages, but not the old ones. So in the case of key compromise, if you're using key exchange for authentication, then it has kind of the surprising thing, is that since you only need one of the private keys to make the shared key, if you use it through authentication and you have my private key, you can use anyone else's public key, and then I'll think I'm talking to that person. So if you use a signature for authentication, then if you compromise my key, you can pretend to be me, and everyone else will notice, oh, Dominic's gone a bit weird. I guess he's been hacked. He's suddenly gone schizophrenic or something like that. But then if you use key exchange for authentication and you compromise my key, then to me, you can authenticate as anyone. So suddenly I think everyone has gone insane. Why has everyone gone so weird? Everyone else has been hacked. I'm the only one left. And then everyone else is like, fuck, Dominic's gone really strange. He's just started being addicted to everyone. I think that is weird. Like, that is not failing safely. That, like, anything, like, that's very strange. You could figure very Byzantine failures that way. So I think we need new crypto protocols. And I sort of started this project on GitHub called Audit-Driven Crypto, where we're basically following this process to develop new specs for abstract protocols. I mean, without choosing the primitives yet, but just being like, how does this thing, what properties should it have? And then auditing the paper design, then later we'll implement it in various languages that are required, and then auditing that is the same as the design. And I think this will be much more understandable and hopefully good. So check that out or talk to me about it later. And also that's an important thing that, like, all of the various protocols we're talking about at DTN basically all need, there's some mid-level protocols that we all need, like secure channels and that sort of stuff. So that's something we can definitely all benefit from, even if we have high-level protocols that depend on different intuitions. Thank you.